Okay, last bit here, folks, about drugs affecting action at the synapse. We've gone over how these drugs can block reuptake and how that's um, how an agonist can work, either remember by mimicking in the receptor sites or by blocking reuptake. That's always going to enhance the effects of a neurotransmitter. Now let's get to the antagonist drugs. And really, there's only one thing for me to explain for this. There's other ways it can work, but this is really what you need to know. An antagonist drug is likely to block receptor sites. Okay, so this time the person ingests a drug, the chemical gets into the bloodstream, swims into the synaptic space, and it's going to fill up a receptor site. But this is a little different than what we've seen before. Let's go back a second. Whoops, sorry. If I can pause it. Nope. Okay, so the last time we saw these drugs go into receptor sites, we saw them mimicking endorphins, right? The circle, drug chemicals, all very symbolic here, fell into the round drug chemicals, fell into the round receptor sites. Okay, this time the round chemicals are going to fall into the triangular receptor sites. Well, they don't fit there. They're not going to engage anything there. That key isn't going to engage that lock. Instead, she's going to gum up the works. This is like somebody sticking bubble gum into the lock. So imagine these red triangles are trying to get to their receptor sites, their neurotransmitters, and they are prevented from doing so. They go back home. Okay, now with prescription drugs, this kind of drug would be given if somebody had too much of a brain chemical in their brain. I'll give you an example of that in just 1 second, but one example of this is caffeine. Caffeine is a drug, of course, one that people use all the time in coffee, soda, what have you. Caffeine is the purple circles here, blocking adenosine. Adenosine, Adenosine. Adenosine, again, I'm going to keep this really simple. Adenosine is a chemical that can make us tired. It makes us feel sleepy. It calms the body down. Adenosine helps with sleep and calming, relaxing. Okay? Adenosine helps our body relax. Check it out. When we drink coffee or Coca-Cola or whatever, the caffeine chemicals go in here and block the adenosine receptors. Adenosine, which is supposed to relax and calm our body, is kept from doing its job. The effect, we feel excited and motivated and stimulated, alerted, whatever, right? When a person drinks their coffee and they feel, energized, adrenalized, on edge, in fight or flight mode, however you want to put it, that's because this neurotransmitter that would have calmed our body down, made us tired, made us relax, that neurotransmitter is being stopped by caffeine, an antagonist drug. Hopefully that's making sense. Okay, here's another example for you. Antipsychotic drugs that are used to treat schizophrenia. Okay, that's a disorder we'll learn about more, most likely after the AP exam, because they're not testing you on schizophrenia this year. But anyway, schizophrenia is a psychotic disorder. It's a psychosis. A psychosis, that's Psychosis, psychosis. A psychosis is a disorder where a person can't tell the difference between reality and fantasy. For instance, if somebody is having hallucinations, they might hear voices in their head that aren't really there. That's a symptom of a psychotic disorder, okay? Or a person might be delusional. They might believe things are happening in their life even when they're really not, like believing government agents are out to get them, or that they're being spied on, or that a person believing that they're in contact with an alien species who is giving them directives on what to do on Earth. These are delusions. A person believes things that are not real. Well, that psychotic disorder can be treated with antipsychotic drugs that do this, folks. Antipsychotic drugs, remember I told you, it's not that antagonist drugs are good or bad, it's just how they work in the synaptic space here. An antipsychotic drug is an antagonist drug. Let's go back. I can tell you there's a neurotransmitter, we're going to imagine it's the red triangles here, in a schizophrenic brain that psychologists think is too abundant to the schizophrenic. Like a schizophrenic has too much of this certain chemical. And it's one that in certain parts of the brain makes us feel really happy. It's dopamine. I told you dopamine's very complicated too, sort of like serotonin. It's complex. It affects different things, different motivations, different behaviors, different functions in different parts of the brain. Dopamine in the nucleus accumbens makes us feel rewarded and excited, but in other parts of the brain, dopamine might affect how we experience the world, our sensory processes, our motivations, things like that. So think about it. And again, this is, simplifying things a bunch. If a schizophrenic patient has too much dopamine in their brain, causing these psychotic symptoms, then they're going to be treated with a drug that's going to block that dopamine. Watch, here comes the antipsychotic drug, blocking the dopamine. The dopamine is sent back to where it came from. The dopamine, in this case, in the psychotic person's brain, the dopamine was kept from coming down here to its receptor sites. So as far as this neuron is concerned, there's not as much dopamine in the brain. Dopamine levels have been balanced out, and this can help treat the symptoms of schizophrenia. Okay, another disorder this is used for, that I hope you find this interesting. And I wish we had our normal class period. I had so much to teach you about this, but you might know something about Tourette's syndrome. It's a tic disorder where a person tends to have movements that they can't necessarily control, sometimes jerky, sometimes extreme movements, and or they can have vocal tics. That's T-I-C-S, tics. Tics are these involuntary, sudden, like impulsive movements or sounds that a person makes when they have Tourette's disorder. You might have seen characters on TV shows or movies that are like, spouting out obscenities uncontrollably. You should know that one, Tourette syndrome is in the DSM-5. It is a disorder that's identified by the APA. It is a tic disorder, a neurological disorder. It's not a psychosis. Tourette's patients know very much what they're doing. They have a very hard time controlling it. There's a lot to learn about Tourette's. But the other thing is the whole spouting out obscenities. It's a very rare symptom. Very, very few people with Tourette syndrome actually exhibit that symptom. It's called coprolalia. It is a real symptom. Some Tourette's patients have it. It's very rare. Here's why I bring it all up. It turns out that Tourette's patients seem to have problems, again, oversimplifying things, in and around a part of the brain called the basal ganglia. Now that's near the center of the brain. We'll learn more about that in the near future. The basal ganglia helps refine our movements so that we can move fluidly and in a controlled way. Well, to put it simply, a Tourette's patient has neurons in the basal ganglia that either have too much dopamine or the brain is hypersensitive to its own dopamine. To put it simply, Tourette's patients have a problem with their own dopamine in the basal ganglia of the brain, and that ends up affecting their movements and motivations and things. Again, that's a simple explanation. But in really extreme cases of Tourette's, folks, Tourette's patients can be given antipsychotic drugs. Whoa. Tourette's is not a psychotic disorder, but in very extreme cases of Tourette syndrome, the Tourette's patient can be treated with an antipsychotic drug. Why would they give an antipsychotic drug to somebody who's not psychotic? This Tourette patient knows exactly what they're experiencing. They're not hallucinating or believing untrue things. Why give them an antipsychotic drug? It's all because it's, the psychobiological approach, the belief that Tourette syndrome is caused by a problem with dopamine. So let's give them a drug that blocks dopamine from getting to the receptor sites. We level out the dopamine that's allowed to do its job, and we therefore treat the extreme Tourette's symptoms. Okay? Too much dopamine in the basal ganglia could lead to Tourette's syndrome. Too little dopamine in the basal ganglia, just FYI, random fact, just so you know, if dopamine starts leaving the basal ganglia, that can lead up to Parkinson's disease. So if neurons start to die off because of Parkinson's disease, they disintegrate, they start falling apart, and the dopamine leaves with them. Dopamine, if it's not in abundance, but if it's in limited quantity in the basal ganglia, it can lead to the tremors and physical symptoms of Parkinson's disease. So a lot of random neurological facts here. I really want you to understand how these neurotransmitters are linked to specific behaviors, and then how these different drugs interact in the synaptic space here with those neurotransmitters, with the receptor sites, to again alter behavior or thinking or mood or whatever. This is all from the psychobiological perspective. Makes a lot of sense to me. I hope it's working for you guys. You gotta let me know if it's not. Okay, so we're about done here on this topic for now. I know these have been long videos. I hope you're chunking them out throughout the week. This would take a lot of class time, but we're missing a week of class with this whole closure, another week of class, I should say, and hopefully this will help you catch up with some of the content. So look here, folks. When it comes to this drug use, we of course have to think what might happen long term. Okay, because look at this. We know that neurons can change based on their experience. We've mentioned that in one of the earlier videos that hopefully you've seen before this one. We mentioned how the myelin sheath can grow on neurons when those particular neurons are used a lot. We also need to know about this thing called long-term potentiation, LTP. Let me explain that quickly before moving on, because this is another example of how neurons are adaptive, how neurons change in response to what they're going through. LTP, long-term potentiation, is very simply a neuron getting better at doing its job, okay? Or we could say LTP is when a synapse gets stronger, okay? The synaptic connection gets stronger, allowing neurons to communicate better. Now, there's two ways that that's going to happen, two things that happen to make LTP happen, to make this connection stronger, to make the job happen more efficiently. That's what LTP does, and here's how it happens. One, the axon will become more myelinated. As we've learned, that's going to speed up the neural firing of the sending neuron, but that's not all. When these two neurons are communicating a lot, here's what researchers have discovered. Dendrites will start to grow more receptor sites. Now think about this. This neuron, this is all what LTP is, by the way. This neuron becomes myelinated, so it gets better at sending its signal, okay? Sending those neurotransmitters fast and efficiently. The receiving neuron grows receptor sites, so it gets better at receiving the message. That's LTP. Complicated idea, but we can simplify it in that way. LTP makes that connection stronger between neurons. And this is all just examples of neurons changing in response to what they're experiencing. Well, now let's go back to our drug point to see how this all applies. If a person's taking a drug, could be a prescription drug, it doesn't have to be an illegal one. If they're taking a drug for a long time, all those, an agonist drug, for instance, right? An agonist drug is mimicking in the receptor sites, or it's blocking reuptake and rebounding those neurotransmitters back into the receptor sites. Either way, the dendrite thinks it's being bombarded with a bunch of neurotransmitters. So guess what's going to happen? That's weird. That's gross. Ew. This dendrite's going to grow more receptor sites to accommodate all those neurotransmitters it thinks it's getting extra. Well, what do I have here? All those receptor sites grow to react to all the supposedly extra neurotransmitters. When the drug is not in the synapse, there could be, again, oversimplification in the way I'm explaining this, but consider it. There could be almost like a neurological craving for that neurotransmitter because you have this connection here between neurons. The drug tricked this neuron into thinking that there were a bunch of extra neurotransmitters there, so it went ahead and grew a bunch of receptor sites. It's ready. This receiving neuron is ready to get a bunch of neurotransmitters, but there aren't really more neurotransmitters. It was all artificial. It was all a trick on the brain. It was a hack. And now we have the effects of that. We've got changed neurons. Changed is the word I tried to say there. We have changed neurons because of the drug effects. And now when that drug is out of the bloodstream, you've got an imbalance of sorts here, a neurological imbalance. A neuron that is expecting a bunch of neurotransmitters, gimme, 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 but the sender doesn't really have any more neurotransmitters to give. Okay? This could be part of what causes withdrawal symptoms, folks. We talked about withdrawal in our different classes, I think. If not, let's go over that quickly. Withdrawal is the physical symptoms a person has when a drug is out of their system. Okay, it could be psychological symptoms too, like irritability, finding it hard to focus, things like that. But also withdrawal can be real physical symptoms like stomach aches, cramps, the shakes, headaches. Well, look, doesn't have to be illegal drugs for this to happen. If you drink a lot of caffeine, if you're a coffee drinker, you know what happens on the mornings. You don't get your coffee. You get the weird headache and you just don't feel right and you're irritable and grouchy. You could have real pains. This is apparently way, way worse for a person addicted to heroin, of course, but different drugs, lead to different symptoms. This could be part of the reason for the withdrawal because the drug use actually physically changed the neurons. Okay, so that when the drug's out of the bloodstream, out of the synaptic space, now when we're back to normal, our neurons aren't functioning normally, at least not yet again, because the drugs have physically changed the neurons. And don't forget, all these drugs are doing, every single drug in one way or another, simply interferes with the natural stuff that's happening in your brain anyway. The drugs are a hack of sorts to the brain, okay? Also, the drug could make the person feel like they need more of the drug to feel its effect. That's tolerance, right? Go back to what we talked about. Because this receiving neuron adapts to what's happening, right? Like eventually there's going to be more receptor sites than there are neurotransmitters to fill them. So we're going to need more of the drug to, have the same effect on the receiving neuron and to have the same euphoric effect, euphoria, the high, whether it's from caffeine or cocaine or heroin. This, you know, adaptability of neurons could explain withdrawal and tolerance. And as we may have mentioned before in class, folks, these two things together are signs of physiological addiction. Physiological, physical, biological addiction. You hear people talk about addiction. We could call this dependency as well. What this means is that the body is not functioning normally anymore. The body has changed. The body has adapted because of the drug use to where, look, withdrawal, the body's not able to function normally when the drug is out of a person's system. And tolerance, the body has changed in response to the drug use to the point now where the person needs to use more of the drug to feel its old effects. This is physiological dependency. I started to say, you'll hear people talk about addiction all the time. Like you can be addicted to shopping or addicted to chocolate or whatever. It's arguable, okay, whether there's a psychological addiction to something. Like maybe a person feels like they have to eat chocolate or go shopping or exercise or whatever. But arguments aside, physiological addiction is when these two things have happened. These are two definite characteristics of a physical addiction. The body has physically changed, neurons have changed in response to drug use for all the reasons we've discussed. So what's the moral of the story? You know it had to happen, right? Get high on life, kids. Be careful out there. You don't need to hack your brain to have a good time. All right? We will have our Zoom sessions this week. I hope you chunk out these videos and get a lot from them. Come at me with questions. Feel free to email me. And I hope to see you soon. Thanks, everybody.